Hey guys, this is Josh Myers, and on behalf of Academia on Demand, I'm bringing you what I hope will be the final video of the covalent bonding theory section of this channel. This idea, we are going to be done with the basics of the drawing of the Lewis structures after this video, hopefully. So in the last video, we went over the idea of the regular structures. So the regular structures, and we remember them to be the linear, and we gave the example of CO2. So CO2. And then we talked about the trigonal planar, which is the three bonds that surround the central atom at maximum repulsion on 180 degrees here. And then so we gave the example of boron trifluoride. So fluorine, and it is 120 degrees. So that is the second regular structure. So three bonded areas of electron density around a central atom. And then finally we talked about let's see if I can fit it, tetrahedral. And the example that we gave was methane, because as we talked about, carbon loves this tetrahedral regular Lewis structure. So this structure simply consists of four areas of bonded electron density surrounding the central carbon. No lone pairs on the hydrogens, because hydrogen only needs two electrons to complete its outer energy level. Okay, so now today we will be talking about here, and I keep saying today, but I'm really doing these videos consecutively, I promise. We are going to be talking about irregular structures. And when I say irregular, I mean structures don't have these pretty triangle geometries. Or these, this is 109.5 degrees. Structures that don't necessarily have the optimal spread of the bonded areas of electron density, or just simply the bonds. Because here, as we know, if there are four bonds around a central atom, the maximum spread can be 109.5 degrees between them. But in these irregular structures, often the bond angles will be less. And this is because of the repulsion of lone pairs. As we talked about, they repel more. So repulsion of non-bonded pairs. Because as we know, all molecules aim to achieve molecular geometry, so molecular shape that is most energetically favorable. And so if non-bonded pairs, perhaps we were to say that they are less stable because they are of higher energy than the electrons in the molecular orbital, because of the idea, hold on for a second, let's slow down here. So as we know from our annotation in a previous video, non-bonded pairs exist in an atomic orbital. So orbitals that aren't the molecular orbitals, so atomic orbitals. And then, as we know, bonded, they exist in molecular orbitals, so molecular orbitals. And as we talked about in the first part of this idea, the first video on this idea, we talked about how molecular orbitals are a combination of atomic orbitals of two different elements, and that they are of lower energy than either of the component atomic orbitals. So what this means is that the molecular orbitals have lower energy. So lower energy. So this means the electrons are more stable, higher energy. And if the electrons are more stable, then they are more able to spread out maximally, as they do in the regular structures, when only bonded pairs of electrons affect the molecular geometry. However, in irregular structures, non-bonded pairs affect the molecular geometry because they are of higher energy they are able, in fact, no, sorry, the physical consequence of their higher energy is that they repel other areas of electron density, such as bonded pairs of electrons, more strongly. So let's get going here. What time am I at? I'm only at a little over 5 minutes, so I'm doing well. Okay, Josh, speed up, because if I ever decide maybe that I want to flip the coin on the teacher job, that sort of go, I need to be able to not bore the kids to death. They don't want to be, I don't want them sleeping in my classroom. Okay, so make this faster. So, okay. Now the first molecule, and I talked about this molecule at the end of the last video, is the molecule NH3. And this molecule is formally called ammonia. Ammonia. Not like pneumonia, not like the lung illness. It is ammonia. So, as we know, as we always do, we are going to find the number of valence electrons. So nitrogen, we know it has 5 valence electrons in its second energy level. So 5 electrons plus, we know hydrogen has 1 valence electron, so plus 3 valence electrons, there are 3 hydrogens. This is equal to 8 valence electrons. And so as we know, if a hydrogen is bonded to a central atom, it is already completely energetically stable. It already has its 2 electrons that it needs. So if we draw the central nitrogen and then draw, as we would, the boron, 3 hydrogens around it, 3 hydrogens around it. These hydrogens are energetically stable, and this only uses 6 electrons. So C2, 4, 6 electrons. So now we've used 6 electrons. Now nitrogen needs 8 electrons to complete its outer energy level. So if it already has 6 electrons, this works out very nicely, because now it can have what we would say a non-bonded pair of electrons only attached to it, meaning it's not part of a bond, because by definition it is a non-bonded pair. So it has a non-bonded pair of electrons in its valence energy level. And so what happens here is that the molecular geometry isn't this. It is not this pretty shape of 120-degree bond angles. What it actually becomes, because of the added repulsion of the outer electron, and the added repulsion of the non-bonded pairs of electrons, it takes on a shape of this. So this is the non-bonded pair. Non-bonded pair. And this non-bonded pair repels the other bonded pairs so strongly that, in fact, even the hydrogens are pushed all the way down here. Pushed all the way down to the other side of what we would say would be the horizontal axes, if we were talking about from relative to the non-bonded pair. So what are the implications on the bond angles? So I'm just going to give it to you, because there's no like magical logical way of deducing this. So this bond angle is about 107 degrees. 107 degrees. So the bond angle has decreased relative to the 109.5 minus 107. It has decreased by about 2.5 degrees. So that's one way that you can remember it very easily. Because really this ammonia resembles a lot more like the methane that we talked about with the 4 bonds than it does the boron trifluoride that we talked about with the trigonoplanar. The reason for this is because, as we are coming to see, as we are exploring this idea of Lewis structures, we are coming to see that the naming of the molecule is all based on the number of areas of electron density around the central atom. And let's draw this as a big rule, because this is very important. So geometry is determined by the number of areas of electron density. You got it right there. Okay, so this is the big rule. This rule has stayed true throughout all of our examples, and so just to make sure that you don't disagree, let's draw out the CO2. So we know the non-bonded pairs exist on the outside atom, so therefore they do not affect the number of areas of electron density, or let's just say the orientation of them relative to the central atom. And so relative to the central atom, there are only 2 bonded areas of electron density, so therefore, because there's only 2, it is linear. Whereas in the boron trifluoride, there is only 3 bonded areas of electron density around the central atom. There's no non-bonded pair, so therefore the molecular geometry is trigonoplanar, and so on. So this starts to become very systematic. We name Lewis structures, we classify them. We classify these Lewis structures based on the type and the number of areas of electron density around the central atom. And I say type as in bonded or non-bonded, and then the number as in 2, 3, or 4. So now we've done this first irregular example, and now we've really seen that this molecule has its structure dramatically changed by the addition of the lone pair. And oops, I forgot to say what it is called. This idea of 1 non-bonded pair and then 3 bonded pairs is called a trigonal pyramidal, and we are starting to get some very confusing names. I don't know how the scientists came up with it, but we have to accept it. Pyramidal. Trigonal pyramidal. Okay, so what is another irregular structure? We are only at 12 minutes and I have to keep updating you, even though you already know because I am looking down at this board. I have no idea what's happening. Ooh, let's not erase ammonia. Let's leave ammonia here. Okay, so let's erase this bottom part. We can probably do it all in one shot right at the bottom. So the next one that I want to talk about is one of the most famous molecules on the entire Earth. It covers about 70% of the Earth's surface, and this is, let's erase this too, and this is water. We drink it every day. We need it to survive. So we might as well know its molecular structure, because as we know, these are completely related. Take my word for it, people. Okay, so, and we know the molecular formula. The formula for water is H2O. So 2 hydrogens bonded to 1 oxygen. And so let's find the number of valence electrons. We've got 2 hydrogens, so 2 electrons plus 6 electrons in the oxygen. So 6 electrons is equal to a total of 8 electrons. Okay, so we have 8 electrons to complete all of these outer energy levels. So we have our central oxygen. Oh no, let's draw it over here. We're going to need some room. Okay, so central oxygen, and then we have hydrogens bonded to it. So let's pretend again that these hydrogens are going to take on a linear shape. They're going to be the only areas of electron density around the oxygen. But as we know, this is silliness, because though the areas of electron density satisfy the hydrogen's outer energy level, the oxygen still needs 4 more electrons to complete its outer energy level and get 8 electrons, just like the number of electrons available to make this molecule. So what we do is that we connect 1 non-bonded pair of electrons to here and 1 non-bonded pair here. And what happens to this molecule is it takes on a shape likened a little bit to this shape. And the overall bond angle is about 104.5. Shoot, you can't have 2 decimals in a number. That's cheating. I am cheating. Okay, so it's not good to cheat, everyone. 104.5 degrees. And as we can see, as we did the last time, this is another 2.5 degree decrease from only one non-bonded pair as opposed to here 2 non-bonded pairs and then 2 bonded pairs. And so as we know, there are 4 areas of electron density around this central oxygen. And so what we call this, we call the 2 bonded pairs and the 2 non-bonded pairs, we call this molecule a bent tetrahedral. A bent, let's see if I can write well here, tetrahedral. Excellent. Beauty. Okay, so we are really starting to see how these non-bonded pairs affect the spread of the angles and thus how we classify this molecule. And this will become very important later when we talk about the net electric force, the net ionic force of a molecule. And what this has to do is the way the bonds orientate relative to each other. We will talk about this. Will we talk about this in this video? I really want to stick to the schedule, but I really also want to talk about other stuff. So I am very spontaneous, I think. I don't know. Okay, yes, let's talk about it really quick. Okay, so as we know, as I just talked about with the net ionic, say, force. Let's call it a force. As we know from physics, because we've all taken physics, I know you have, don't even lie, you've taken physics. And we know that force is a vector. Force is a vector, which means that it has a magnitude and a direction. So, if we look at the methane molecule again. Methane molecule, CH, and this is a regular structure. So, regular structure, we know that each bond angle is 109.5 degrees. It is maximally spread. Well, one of the implications of any structure being maximally spread is the idea that if all of the surrounding atoms are the same, therefore the net ionic force is equal to 0. Ionic force equals 0, we would say newtons, but let's just leave it for 0 for now because it doesn't matter, it's 0. The reason for this is because when they are maximally spread, this force, this idea of the hydrogens pulling on this molecular orbital this way and this way and this way and this way, because they are maximally spread, all of these arrows that may represent force, these electrons being pulled in one way or the other, they all cancel out, because when it's a vector, when vectors exist in opposite directions, let's talk about vectors for a second. If we said that I am big strong Josh and Josh is going to apply a force of 200 newtons, that's a big force, to this table right here, this table. I am applying 200 newtons of force. If we know about Newton's third law, that each force has an equal and opposite reaction, then therefore I am applying 200 newtons to the table, and then the table is applying 200 newtons to me. So 200 newtons to me, but also to table. Okay. And so what's happening here is if I draw my fist, no, bad fist. Bad fist. Okay, fist. Okay. And then we have table. And I've got my force going down this way. The reason why the table doesn't collapse, or that my fist doesn't keep accelerating through the table, is because the table is applying an equal force back in the opposite direction of the force I'm applying. And that's why when I hit my fist on the table, it hurts. Well, the same thing happens in this molecule. Because the electronegativities of all of these hydrogens are the same, they have the same pull on the molecular orbital electrons. So if they have the same pull and they are, again, regular structures, they are maximally spread, all of the force, this pulling force on these electrons, it cancels out. It goes all the way to 0. And this makes this molecule very stable and not reactive. And as we will see later, it also makes it have a lower boiling point. Sorry, a lower boiling point and a lower melting point, because as we will see later, these things actually depend on slightly different factors. So now that we've given that lesson, we can actually do something really interesting here. What we can do is say this same structure persisted. And I know I'm disorganized, but I kind of come up with things on the spot. And I hope you understand as learners that it's hard being a teacher too. So if we take this structure with the 4 bonded pairs of electrons around the central carbon atom, if we take this bonded pair, then what we know is that that these normally cancel out when all of them are hydrogen, but let's just say I replace this with Cl. Because we know Cl has a much higher electronegativity than the hydrogens, then it will pull the electrons much more its way, and this will create a net ionic force. And because my camera is running out of battery right now, I'm going to have to end this video right now, but I will see you later in the next one. Goodbye, everyone.